Hey everyone, it's Sam here from This Week in Machine Learning and AI. What you're about to watch is the recording from our first ever online meetup, where Josh Minella presented Apple's CVPR Best Paper Award winner, Learning from Simulated and Unsupervised Images through Adversarial Training. We hold meetups monthly where we cover classic and hot papers in machine learning and AI, and we'd love for you to join us. If you haven't registered yet, hop on over to TWiMLAI.com/meetup to sign up. Enjoy the meetup.
Okay, cool. So, thanks everyone for coming. Today I'm going to talk about the Apple's paper at CVPR, which I attended the talk at a couple of weeks back, it was really cool. Learning through simulated and unsupervised images through adversarial training. And this work is again by Srivastava and some others. I'm going to present it, and my name's Josh. So I guess we'll start. What are we going to talk about? First, I'm just going to introduce myself. Then I'm going to talk about the motivations behind this paper, behind some of my own motivations, why I think it's cool, and why machine learning in the future will be benefited by this. Some of the methods they use, like the actual the ideas, the networks, and some of the equations that went into it. Some of the experiments that they talked about. In the paper, if you did read it, they noted two different experiments, an eye-gazing experiment as well as a hand gesture experiment. I'm probably just going to talk about the eye-gazing experiment, but I might move over to the paper itself and show some pictures from the hand gesturing as well. And then after that, I have some introductory discussion topics, so I might kick some stuff off. But again, if other people have questions, please post them in the Slack. I'll try to have the Slack on my phone right next to me, so if any questions come up on the channel while I'm in the presentation, or if anything seems unclear, I'll try to answer it. And I'll be in the Meetup channel, by the way. So just a quick introduction to myself. I'm a machine learning engineer at Argo AI. We're a self-driving car company, and I work on more or less the perception side of machine learning for self-driving cars. So really, it's when you look at the world, where is a car, where is a person, where are they going, stuff like that. Previous to this, I worked on the Uber self-driving car, also in a more machine learning type role. Before that, I was at Facebook, where I was building hardware, switches, and servers. It's very different than machine learning and AI, but there's actually quite a bit of knowledge I learned from that carries over. And also Amazon, where I was writing software. I went to school at Michigan Technological University, a degree in computer engineering. And besides a machine learning engineer, I also consider myself a roboticist, where I solve machine learning problems through the eyes of a roboticist, since a lot of my background is more on the robotics practitioner level. And for some of my background experiences is why I really enjoyed this paper. So let's talk about some motivation. First let's really define a problem, right? Let's define this problem called eye gazing. So let's say that you have an iPhone, and the iPhone is looking at your eyes, and looking at your eyes to the camera, and you're moving your head around, and it finds your eyes, but it's trying to figure out where on the screen your eyes are looking. This is essentially the eye gazing problem that we're talking about. So you get all of these images over here of eyes, and you're basically trying to find where in space these eyes are pointing. Now, it's really hard to get this data, right? You're going to have to get data to train a machine learning algorithm, or train whatever algorithm you want, whether it's machine learning or not. You pretty much have to take pictures of a bunch of people's eyes and also calculate where they're gazing, right? They'll have to, I don't know, look at a wall or something, and you'll have to figure out exactly where they're gazing, and that takes a long time to get data. So this bottom row over here, this is synthetic data. So imagine if you took a video game basically, and took pictures of people of 3D characters' eyes in video games. That's what all these are. And it's a lot easier to generate that sort of data, right? Because it's synthetic data. I can make the 3D video game character do whatever I want, look in whatever direction I want, and get perfect eye gazing characteristics. But the really annoying part is that these, like up here, these 3 eye gazing image examples, these look real. And as a person, like these bottom synthetic images, they look pretty good, but you can tell pretty easily they're fake. Like the skin texture is like very perfect. There's almost no imperfections in what's happening. And when a machine learning algorithm tries to learn off of these synthetic images, it might do poorly on real images. So you can always mix real and fake images, but then you'll get kind of this bimodal distribution. You'll get uneven data in your data set, and it might confuse the algorithm. So really, what is this motivation? What do we want to do? We want to take this synthetic data. We don't want to throw it out, but can we make it look a lot like the real data somehow? Can we throw the synthetic data through an algorithm and make it look extremely realistic? Because we have this data generator already, we might as well make use of it. And we have some pieces of real images, and we want to use those some real images. So how do we put these together? Well, that's what this GAN is for. So before I give you the answer, one of these rows is real images of eyes, and the other row is actually fake image of eyes. So I want you to take a second and try to guess which is real and which is fake. And I guarantee you it's going to be probably pretty hard because they both look very realistic. So I'll give you a second if you want to really like try to stare into the images, because I couldn't figure it out. So in 3, 2, 1, this top is real and this bottom is fake. And this is really good. Actually, so inside of the paper, Apple actually surveyed a bunch of people and gave them these real eyes and these fake eyes. And they actually, people, statistically speaking, could not tell the difference between the real and the fake, almost like what they define as a visual Turing test, which I think is incredible. That's really awesome. And also for a machine learning algorithm, that's perfect. If people can't tell the difference, then I can add all of this data into my algorithm and train much more efficiently with much more data and have hopefully a better algorithm. So really what this all boils down to is, can we create a network or an algorithm or anything to refine these fake images? So I just want to give a little bit of vocabulary first. These computer generated images on the top here, these are what I will call synthetic images. These are coming out of some 3D video game character algorithm, right? And these bottom here, these come out of the algorithm talked about in the paper. These are called refined images. And then real images, which I haven't shown yet, are actually just real, right? That's what we saw before. These are real images. Okay. And then something else that's really neat about this, before I get into the specifics, notice how the gaze direction in the synthetic and refined images has been preserved. This gaze direction is kind of straight, this direction is kind of straight, this direction is looking a bit, it's a light right in the middle, this one's not as good, but it's still not terrible. This one's looking up, and this one's also looking up. And this is critical in this transfer, because if you change the gaze direction, you refine the image, then it doesn't matter anymore. That the label for that synthetic, for that refined image is pointless. So it was really important that they made sure the images had to match, at least in a gaze direction or whatever their business case is. So what they ended up coming up with was this thing called SimGAN. So, and the network that they used to actually create these refined images is what's called the refiner network, because it refines. So essentially, a refiner takes in synthetic data, it looks at real images, and bada bing, bada boom, gives refined images. And notice how these real images are unlabeled. It only looks at real images just to get what an eye looks like. So you don't have to label these real images, which is really neat. I don't have to get all the fancy gaze direction anymore. But of course, how do you actually train it? You're not going to have a person telling the refiner network, hey, this is a good image, this is a bad image. How do you actually train a refiner network such that it knows it's done a good job? Well, really, the GAN, or the generative adversarial network, does what I just did with you. We can create this discriminator algorithm or discriminator network, whatever, whether it's a neural network or not doesn't really matter, that tries to decide if the refined image is real or if it's fake, or if some random image is real. So as like a high level pipeline, right? So you have some simulator, some 3D video game simulator, generates a synthetic image, goes through refiner, creates a refined image. The discriminator is given some random real image. And it has to decide, is the refined image real or is the real image real? And then if it gets to the point where it can't figure out whether the refined image is real or the unlabeled or the real image is real, it doesn't know which one, then you know the refiner is working. So essentially the discriminator says, hey, the discriminator tells the refiner which one it thinks is real, and the refiner takes that into account. It says, oh, I did a good job, I fooled the discriminator, or oh, I did a bad job, I didn't fool it. So really the discriminator's job is the refiner's job is to trick this discriminator and help it learn what a good refined image looks like. But the question is, okay, so this is like a very high level overview of just how this pipeline works. How do we actually train this thing? How do we actually train the refiner, and what do the loss functions look like on this image? So let's go over to training the refiner. So the refiner, like I said, the refiner finds is trying to map the synthetic image to the refined image and also keep the gaze direction. Now this is very important. This is what the subtraction sign is up here. It essentially, as part of the refiner's loss function, tries to align as many, I guess you could say, pixels as possible between the synthetic and the refined to try to keep the gaze direction. And that's just this bottom part over here. This basically says the subtraction between the refined image and its own image and the L1 norm, or the error, plus what is this other piece? This other piece is how well did I trick the discriminator? So in a different perspective, the total loss, how bad the refiner did, is the sum of two things. How well did we trick the discriminator, plus how close are we to the original image? Where this is essentially the probability that the discriminator thinks it's a real image. So, if it's a fake image. So if this is 1, or if this is very high, then the refiner did a bad job. And of course, if this is very high, the refiner did a bad job. So we want to minimize both of these things together. So now let's look at the discriminator. So the discriminator, so far I've been talking about the discriminator as this network, or this thing that just gives out a single 1 or a 0. Just is this image fake or is this real? But if you do that, then what's it called? Yeah, so if you do that, the discriminator could be tricked by like little parts of the image. Like let's say there's a little part of the image that's not doing so well. It might figure out it's fake, but then the rest of the image looks perfect, and a person might not even know that. So what we essentially do is the discriminator blocks out the image into regions. So it says like this part of the region, there's a 20% chance the image is real. This part of the region, there's a 50% chance that the image is real or image is fake. And this local loss, helps the refiner, or when I say D and R, I refer to discriminator and refiner. This local loss helps the refiner from missing small details in the image. So the discriminator can basically say, hey, refiner, you're doing a good job making a fake, pupil, or a pupil part of the image, but you're doing a really bad job trying to make a fake bottom left part of the eye, or this little iris part. So it can help the refiner just like tweak the individual pieces of the eye image. So now what does it mean for the discriminator to do bad? What is the loss function on the discriminator? Well, if we take a step back, what's the discriminator doing? The discriminator is saying, is this a real image or a fake image? So the discriminator itself is doing well. when it isn't tricked, right? The discriminator's job is to not be tricked. It's like the discriminator needs to be really, really confident that it has not been tricked, and it needs to give the refiner as much information of how bad it did as possible. So if we take the probability that the refined image is synthetic, right? This basically says, is the refined image fake? Plus the probability that the real image is real, which essentially says, am I sure about if the real image, if I know the real image is real, then the discriminator is doing a good job. And if the discriminator knows the refined image is synthetic or fake, then the discriminator is doing a good job. But you want to minimize this. You want to make sure this is small. You want to trick the discriminator. You want the discriminator to do really bad. So let's see. Let's go to a higher level overview back over here. I skipped this part just because we haven't gone into because I already went into the loss functions of the refiner and the discriminator. So I just want to revisit just the overall training of this system. So step one, we sample a small batch of synthetic images where we just grab some images from the simulator. And then we run these synthetic images through this refiner, and we get refined images. And we calculate a loss on the refiner, and we train the refiner, we make it better. Now, no, we're not training the discriminator right now. We can't do that, or else, because we'd have this circle. You can't train in a cyclical network. So we're just assuming the discriminator has been trained, it's all good, and we're just using it as is. Right now, we're training the refiner using the discriminator at the start. The refiner creates a refined image. It checks the differences between the synthetic and the refined. It asks the discriminator, hey, can you guess if this is a refined or a real image? The discriminator says yes or no based on different pieces of the image, gives that information to the refiner, and then the refiner keeps training and training and training. And we do I think they do 2 or 3 loops, some small amount of loops. After we do that, then we sample a new batch of synthetic and real images, and then we train the discriminator. And now we hold the refiner constant, because again, we can't train the refiner and the discriminator at the same time. We have to make sure we train one of them at a time. So we hold the refiner constant, train the discriminator. We basically run a bunch of images through the refiner again, get a bunch of refined images, get a bunch of real images, and try to make the discriminator as good as possible at classifying images, as of course, real or fake. And we do that a couple times. Again, I don't remember exactly how many times, but it was only a few. And then after we do that, we go all the way back to the beginning, and we repeat this process over and over until until one of two things, or a few things happen. One, just some large amount of time. 2, you could look at the refined images as a person, right, and give a visual Turing test again to see how well they're doing. Or 3, another metric you could use, which they show off they actually don't show it in the paper as much, but they show it in their blog, which I can post the link to. You can actually look at when the discriminator is 50% right and 50% wrong if the image is refined or real. When the discriminator is completely fooled, completely baffled, then there's no point in going anymore. I guess there's a little bit of a point, because the refiner will still gain could still train off the difference between the synthetic and the real information. But besides that, you're pretty much done, because we're using this discriminator as the end all. Is this image refined, or is this image real? So this is kind of the overall training of this whole system. And now I'm going to go into some more some of the experiments that they did. And again, if any time while I'm talking you guys have questions, please post in the Meetup Slack group. So let's skip over. So let's look at some eye tracking experiments. This is just one of the tables that they supplied in the paper itself. You can see that this R/S is with real and with synthetic data, and these are all just different algorithms trained for the eye tracking task on real data. And then notice how on the synthetic data, does extremely well on the error. Let's see. So we got some questions popping in. Sam asks, is the idea here that we're eventually going to be able to create a ton of labeled refined images for each synthetic image? Probably for each, yeah. So we're assuming that the question one more time, is the idea here that we're eventually going to be able to create a ton of labeled refined images for each synthetic image? So each synthetic image should create, in an ideal scenario, like just one refined image. What we're talking about in this loop, this is purely just training. As soon as we know that the discriminator and the refiner are completely trained, we don't need the discriminator anymore. We assume this simulator is just going to be spewing out a bunch of random pieces of synthetic data. And each synthetic image is then going to be refined and then used in some new data set. So yeah, I don't know if that answers your question, Sam. Okay. But I guess, yeah, we can talk about that a little bit towards the end. Let's keep going. So again, on the synthetic data, so the synthetic data with this algorithm, the eye tracking task performed very well. It performed very well versus other KNNs and convolutional networks and forests and whatever. And this algorithm with a convolutional network did well, even compared to other convolutional networks with real images. Note, this is a CNN with UT multiview. I don't remember. I think this is a data set because this is real images, but I'm not too sure. But the CNN with multiview on real images did much worse than the CNN with the Unity as refined images. Although what I'm personally a little confused about is I don't know if this UT multiview is a public data set. If so, I would have wanted to see them run the CNN with UT multiview synthetically altered images, but I'm not sure. That's a question I could probably ask him. Although, not to trail off too much, but when I went up to the booth to ask them questions at CVPR, they said in a very Apple way, like, "Oh, we can't answer that question. This whole public facing thing is new to us also." So, yeah. So, anyways, some more eye tracking experiments. Again, like I said before, people weren't able to tell the difference. Like, this quote, like I just copied and pasted, I think is really cool. In our aggregate analysis, 10 subjects chose the correct label 517 times out of 1,000 trials, meaning they were not able to reliably distinguish real images from synthetic images, or synthetic. And they also did I think somewhere in the paper they did another study where they directly asked the same participants to distinguish between the synthetic and the real images, and they were reliably, with high percentage, able to distinguish them. So from a statistical standpoint that this did work. It did work to whichever people they sampled. But I mean, as humans, even regardless of how much they cherry pick for the paper, it looks pretty cool. Like, you can see again, these are the synthetic images, these are the refined images, and these over here are some real images. Now, I guess maybe this example is not as good because, I think I could tell a little bit difference because these are kind of blocky, but these all look pretty real. Like, I would not be able to tell the difference. But yeah, so I think this is all this is pretty neat. Something else I wanted to show you before we get into the discussion topics is when I switch, can you guys see my screen? If I change screens real quick?
Yeah, we saw it.
Okay, you did see it. Okay, good. Let's see. So I'm going to switch over to the paper. I probably should have added this. Oh, thanks for saying yes on the Slack. So let's see. Where is it? Sorry about this. I just remembered this, and I wanted to include one more thing, but something else I didn't include. The refiner. The refiner actually they found out that the refiner needed a history of images, not just like a single image at a time. And my algorithm I talked about before was slightly altered just because the algorithm also takes into account how well have I been doing so far. And and you can read the paper for more specifics, but this image just shows that like when the discriminator gets history, how the images change and how they don't change, how they change without history. And you could see they're a lot better with them without history. And then besides that, I think there was one other thing. All these hand stuff, these are just the hand gazing, or sorry, the hand pose estimation experiment, which is another experiment they did that yielded very similar results. I think, though, that that's all I wanted to talk about right now. So let me get into my discussion topics. I don't know if I went too quickly, but so some possible discussion topics that I have right now. What else could this be applied to? Really, I mean, anything where, to kick that off, synthetic data is hard to come by. This can be applied to. Did anything confuse you? Please post that in the Slack again. I'll try to clear that up. Like just as like a thought experiment, what do you think would happen if you got rid of that extra loss near the top of the refiner network? And then finally, what happens when you add memory to the discriminator? I talked about that a little bit, but for now we can leave that out because I didn't go too far into it. So I guess real quick, I'm just gonna, before we get too close, I'm going to look at the Meetup stuff. Let's see, Dwayne Cornish. Does anyone know if they trained on left eyes and right eyes separately? The refined image in figure 6 seems ambiguous to me. Is that nose on the bottom left or bottom right? Or is that nose on the bottom left or bottom right? Or did the refiner learn to make it left-right ambiguous? Let's look. So I know in the paper itself, let's see. No, sorry, that was a little bit annoying to people. Yeah, so here's a bunch of images. So the question is it left-right agnostic? It looks like it. So it looks like it does actually have left or right, personally. Just because, like, you see this little, I don't know what this is called, like the inside of the nose, but the small part of the eye near the nose. But the synthetic data definitely had left or right. So I would assume that the network would learn to differentiate that. But I don't know. I mean, there is some noses here, but yeah, I can see how that might be a little ambiguous or confusing. So the next question, Teddy asks, is the history stored separately from the refiner, i.e. is there a new refiner created for each image pass? There is not a new refiner created for each image pass. It is the same refiner that gets, it is the same refiner that gets trained. I believe that the memory comes into play. Let's see. Yeah, so the memory comes into play I think they're just either, I don't remember if they're storing images or I think they're using like an LSTM layer to keep, to keep a history of the weights. Oh, sorry about that. Yeah, they're actually using, right, I remember now. They actually use a buffer of refined images to help with the refiner, but the refiner stays the same every single time. Let's see, what else do we have? At K-Mater is on a walk us. Oh yeah, so I'm not sure. Yeah, K-Mater, I'll probably ask you in a little bit because you had like some visualization or a really quick example that you could walk us through. Maybe we'll revisit that in a second. Let's see, Dry L. Wilson. This seemed like a good way to create realistic character images in a gaming simulation. Start with synthetic royalty-free image, use the refined data gathered from a very large real population to create synthetic characters. I mean, yeah, no, that's definitely a pretty cool cool way to do it. I don't know, like really, I think this could be good for anything, anytime that you just need data and it's hard to get data. But I guess at this point, we're into, unless people have more just like straight up questions, we're into a bit more of the like discussion part of things. So I don't know if Sam, you want to talk for a second and describe how you want the discussion process to go, or if I should talk about it. Oh, actually, I guess we have one more question. did they compare performance against just adding dumb Gaussian noise to two synthetic images? I don't know. That might be a good. I don't think they did, but like I think it would probably do a little. It could do a little bit better, but I don't know if it'd do perfectly better. I mean, in my experience, like I've come across that a lot where I just like I've tried to make images look more realistic by like changing the lighting or adding Gaussian noise or adding like changing the hue values here and there, and they do a little bit, but this did like so like I guess from a practical perspective, I have no data I guess to back up what I'm saying for this, but they just did so much better than the previous benchmarks. I think that this would have done better than Gaussian noise, but maybe that would have helped. Yeah, so how is the gaze direction fixed while generating data? So that's what I talked about over here. Let's look at this. Where are you? Yeah, so when you're training the refiner, okay? So when you're training the refiner, it takes into consideration in the loss function of the refiner, the absolute pixel differences, like the softmax pixel differences between the synthetic and the refined image with the subtraction loss. And that inherently, for their application at least, tries to preserve the gaze direction. Because, you know, I guess at a very, very high level, right? The pupil is dark, so all the dark pixels should be together, and versus like the white pixels. Let's see. I'm a bit unsure of what is meant by adding history in the R. I assume that it's a neural network, and the training is iterative, D to R to D. The history is stored implicitly in R itself. Let's see. I'm trying to remember exactly how they stored the history. I think what they ended up doing, let's see, history. So I think what they actually ended up doing, stability of training by updating the discriminator using a history of refined images rather than the ones from the refiner network. I think they just updated, like, they just had like a buffer of images that they had the discriminator look at. Here we go. Let's see. Yeah, so let's see. Refined images with current R. They create a mini batch for D defined, and then I think, oh, I see. As part of the mini batch for D, they added some of the refined images back into that mini batch that it would iterate on. So I would read the paper for more specifics on that. I'm sorry if I couldn't answer that as well as you want, but from what this diagram sounds like and from what I remember from the paper, I should have read it a little bit more recently. I apologize. They kept that buffer of refined images from previously, and then they stored some inside of the mini batch that is created to train the discriminator. So let's see. Is there a method for finding, oh, hold on. I'm trying to catch up on this question. If anyone would like to ask a longer cute question via voice, just type here and we can call you on first. Oh, sorry. Yeah, so if anyone has been reading, if you type here into the Slack, then I'll acknowledge you, you'll unmute yourself, and then we'll add you to the discussion, or you can ask a question, make a comment, whatever. So Dwayne Cornish says at Gen Z, oh, I think he just answered you. Yeah, it's my understanding is that R is changing over time and D is changing over time. So as R changes, D starts to learn those changes. Anything that ever came out of R should always be labeled as synthetic for D. However, if D is only seeing newer images from R, then it stops seeing some of the older synthetic images. Yeah, I mean, that's pretty much it. So history equals refining same pictures on several times. No, history is just like keeping essentially a buffer of those of previously refined images, and then having D run its back propagation on them every so often. From what I understand, again, I haven't read the paper in a couple of days. I've just been very swamped, but yeah. So, and as far as history is concerned, the paper goes into it in a little bit more detail, but let's see what else. So yeah, I think we have some more people who are asking questions. Some other things that are interesting about this paper is you also have these like synthetic and refined hand pose images, and you can see that. I mean, I guess all the algorithm really did was just kind of make them a little bit blurrier. So in this case, it wasn't as impressive, which is why I didn't show it, but it's still a really interesting paper. Yes, correct. So Dwayne Cornish just posted, history is a random selection of images that came out of R from previous iterations. Correct. Yep. Yeah. So Dwayne's got it from, unless I don't have it as well. But yeah, and some other stuff I didn't talk about in the paper were just some of the implementation details, but they're really for D and R, but they're essentially just fully convolutional networks. The specifics of them don't matter as much. Ocampo 2209. Oh, sorry about that. Yeah, I just missed it. Is there a method for finding the optimal size of localized adversarial loss for the D function? Curious how this size and the size parameters. So I'm also very nitpicky with this type of thing. Whenever a coworker comes up to me and asks and he gives me an algorithm and there's like a magic number, I'm always the first person to be like, where did that magic number come from? So it could, I don't remember exactly where it came from, but it could come from anywhere, being they just picked it and it worked, or they did k-fold cross-validation where they had like some sort of a validation set and they varied the size of those boxes until they found the minimum amount of error between the sizes. I'm unsure about what is considered to be the optimal size for those localization methods though. Usually they'll just say k-fold cross-validation. In reality, not a lot of people do it. A lot of people say like, this worked because I picked it, unfortunately. But they could have done something smarter. I don't remember exactly. No problem. So I think history is used to avoid R reintroducing artifacts that tricked D in the past, and then D forgot about them after a while when R stopped using them. Yeah, that's some decent, yeah, I think that's some good insight. Because if the refiners create some weird artifact, and you want to keep telling D about it, just so that D can can keep telling the artifact, keep telling R that, hey, this artifact you created is a bad artifact, right? And keep reminding R of that so that it can get to its destination faster. So yeah, let's see. I think, yeah, so we have a few more questions coming in. Is there anything else that's interesting? Here. Oh, this is something I should have talked about. So this is the difference between, so this is in the hand gesture data set, and these are two, these are two refined images. And this shows the differences between the global adversarial loss and the local adversarial loss. And notice how in the local adversarial loss, you have much more refined image on the refiner. Just because like the refiner learns about those much smaller nitpicky things, whereas when you do global adversarial loss, whereas you say like I am 20% sure that this image is correct, that this image is fake or this image is real, then you get these much more bulky like sections. So, and then I guess this kind of circles back to Sam's question, can't I just add like some Gaussian noise? You can, but then sometimes machine learning algorithms are very, very particular about like what type of noise you have. Like we have like over here, you have a much cleaner edge and like these little very high, like these high frequency little bumps over here. And over here, you have very low frequency bumps, and it's a lot less smooth. So even though these look very similar to us as people, a machine learning algorithm might pick up on these things and do a little bit worse. Yeah, so they talked about L1 for self-regularization. So I think they chose L1 just because they didn't want to kill the weights. They didn't want to kill the weights as fast. I think, yeah, so L1 is used very commonly in a lot of more classical image processing approaches. I think they gave their, here we go. I even highlighted it. Let's see, L1 or, so let's see. I remember they talked about it. Let's see, here we go. Yeah, self-regularization. When the synthetic and the real images have significant shift in the distribution, a pixelized L1 difference may be restrictive. Oh, right, yeah, because in such cases. Yeah, because if you had an L2 norm in this case, you would know like how far away you were from the right answer, but you don't know which way. You don't know if I should be like, darker or lighter. L1 norm, I know if I'm darker or lighter just because it's like a subtractive difference. Are the generator and discriminator deep neural networks? If so, what kind? Yes, the discriminator and the generator are both deep neural networks. They're just fully convolutional. They're just fully convolutional networks. They talk about their exact implementation of the paper somewhere here, but yeah, they're just standard fully convolutional networks. I don't remember if they used like an AlexNet or an FCN or whatever type of network, whatever specific type of network they used for the backend, but they're just one of the convolutional networks. I can just search for some words like AlexNet or FCN. Let's see, ResNet maybe. Here we go. Yeah. So with ResNet blocks for all, we use a fully convolutional refiner network with ResNet blocks for all of our experiments. So if you're unfamiliar, ResNet is a type of, it's like a convolutional network that has these like skip connections. I would just Google ResNet. ResNet if you want to know a little bit more about that. Or you can just message me if you have other random questions. Yeah, actually, that's really interesting to note, JC. Their blog is also really, you should also read their blog if you think the paper is a little bit dense, which really it's not terribly dense. Their blog does a really good overview of everything I just said, and then even some better, some better descriptions and a good high-level overview of the work that they did. So let's see. If anyone else has any comments, again, you can just post here inside the meetup. I don't know if I have too much else to talk about. I know that they mostly stayed in the black and white world, but they did a little bit with color, and you can see that over here. So let's see. Does anyone else, I guess here I can open up the floor to this. So does anyone else have any other ideas as to like what this could be used for maybe?
Hey, Josh, why don't we let Kevin jump in and take a few minutes to walk us through the implementation that he put together.
Oh, cool. Yeah, I didn't know he was all, I didn't know he was all set up. Yeah, let me.
Are you on and ready for that, Kevin?
Kevin, maybe he can't hear us.
Or maybe he's muted.
Yeah, that's possible.
Can you hear me?
Kevin, are you muted?
I just heard something.
Okay.
No.
I barely hear you.
My microphone seems to be problematic again. Is that better?
That's a little better, yeah.
Okay, I can try holding it right next to my mouth.
Okay, so yeah, Kevin, just let us know when you're all set. Yeah, I can unshare my screen. Teddy, I'll respond to your message over the Slack personally. Let's see. How do I? Hold on, I'm just trying to figure out how to unshare myself.
I think at the top of the screen. Oh, let's see. I can switch it here. Okay. So we should all be seeing Kevin's screen now.
You see things. Can you see my screen and hear me?
Yes.
Is that working? Perfect. Okay.
Yep.
So the link is in the Slack. If you click on it to go to the Kaggle data set. And so basically, it's this eye gaze data. And so what we put together was more or less all the data that you need to kind of reproduce generally the results that they had. Because when you look at sort of this Unity Eyes project, this is a Windows-only tool. You need to set it up with the right parameters so it produces all of these images, and you end up with hundreds of folders with thousands of JPEGs, which is not necessarily the best starting point for trying to actually train these models. Then you have this data from sort of the Max Planck in Germany, and you get data in sort of another format that's also not particularly easy to use. So what we did for this Kaggle is really package that together as HDF5 files so that you can actually start looking at it and playing around with the data. And so HDF5 is just a file format that allows you to store really large arrays in kind of one compact place and have a number of different fields that sort of explain what's in there. And so for this, we have sort of the gaze.h5 and the real gaze. And so if you go to the notebooks or the kernels, you can look at one called iOverview, where you basically open the HDF5 file, the gaze one, you see that there's image and lookvec. You can then show sort of what are all the images that you see and make sort of figures like they had in the paper. And now you have this lookvec, which is, 50,000, because that's the number of images here, by 4. And what we do is just go through all the different lookvecs to kind of show you. So this is the left-right look. And so this is the minimum value. This is the maximum value. This is one in the middle. And then you have the up-down look. And so the down, the up, and then somewhere in the middle. The other two ones, I wasn't really sure what it is, but it's probably not very important for getting started. We then have the sort of actual SimGAN notebook, which is the much more interesting part, where it's a slightly simplified implementation of what they had, but basically it's the models that they use built up in Keras, combined with this data to actually train it. And so you can actually see how is the data loaded, what models do you use, what's the batch size, what are these D and G coefficients that we talked about earlier, what happens when you actually change them. And then of course a lot of utility functions to get everything to work correctly. And so here we have sort of this image history buffer, which was mentioned a couple times through the paper to keep track of sort of the record of images that we had. We then have the actual networks here. And so here you see it's very clearly a ResNet. You have these ResNet blocks with convolutions, activations, convolutions, and then these addition layers to combine them. You then have 4 of these blocks sequentially, and then this final output. You then have the discriminator network, which kind of does convolutions and max pooling. And then you combine the different models together. And this starts to get a little complicated because you're trying to bring both of the models together so that you can sort of train a refiner and a discriminator model. And with Keras, what's nice is you can just print dot summary and then you see exactly what you've combined together. So if we go down here after the error messages, you can actually see the input layer, what was the size, how many parameters were there, and what else, what is it connected to? And so you can quite easily go through and see, here you had 64 kernels. You could change that to 96 or 32 and see how the performance changes. You then sort of have the other discriminators and then the whole model together. You have the total parameters for the whole model. You then, if you've done this on your own computer, can run this visualization with model to dot to actually see the drawn out topology. This doesn't work, unfortunately, with Kaggle. And then you can define sort of the loss functions. And here they're defined directly in TensorFlow because you have a bit more flexibility there versus being defined in sort of Keras, which is the ideal way to have it. But we have the sort of self-regularization loss where we have sort of these two terms together, and then the local adversarial loss. You can then select sort of the optimizers and everything that's needed for compiling the model, then set up the data generator so it actually provides the models with data to train on. So this is sort of the X and the Y components that are fed to the fitting functions. You then do a very quick pre-training on the data to kind of see what the results look like initially. And then you can kind of do the full batch of training where you run it over many, many iterations and you train everything in the right order. So as kind of the paper showed, there's a number of different steps which you do to train the model. You don't just train everything at the same time. You kind of improve the generator and then you improve the discriminator and then kind of run that iteratively. And this is more or less what's done there. And so you can see this output where you see kind of how the models looked at the very initial stage. And then after training it 20 steps, which is of course very little in the deep learning world, but an example, you see it kind of starts to get better at looking at those final images. And then you can save all of the model weights so that you can reuse them or load them. Kaggle isn't obviously ideal for training really large, complicated models because you only have a limited amount of sort of training time and the computers aren't very powerful. But it's a really good way to show that actually the model you built works and share it with other people because everyone starts at exactly the same point and has access to exactly the same data. So here was a second notebook, which was just trying to get an idea of like what the simple basic models are. And so this one uses a random forest to try to predict the eye direction. It's kind of a starting point so that you can compare that to the SimGAN to see how well that works. So that was more or less what I did. I guess you can ask questions in Slack or whatever, and I can give the screen back to whoever wants to take that.
Josh, was that question for Kevin?
Yeah, I guess that was for Kevin. I was just like curious. If you got rid of the self-regularization loss and you got a bunch of images, did you just see what they looked like? Or what happened? Just curious, just out of curiosity. Oh, I think you're muted.
Yeah, I haven't played with it that much and changing the terms. I've tried it with a couple other data sets, but it's clearly, I mean, it's all there. It's very easy to tweak. There was another question about whose code is this? It's not, of course, the author's original code because they didn't make a repository as far as I know, but it's a fairly accurate recreation based on the papers.
And so your recreation?
I borrowed some of the things from a GitHub repository, but it's more or less my recreation.
Got it. Any more questions for either Josh or Kevin? All right, then. So I will end the video portion of the call, and I will be sticking around on Slack. The Slack will remain for any further comments and feedback. Thanks, everyone.
Yeah, thanks. And if anyone has questions, just shoot me a message on Slack. I'm Jay Manella.